Hello.
Good morning or good afternoon.
Good afternoon. How are you?
Good, good. How are you?
Thank you. Very good. And welcome to our organization.
Thank you so much.
Okay.
Thank you for inviting me. I wish I were there and not here.
Okay. Very nice. And I will start in 2 minutes. Okay. Is it okay for you?
All right. Yes.
Okay.
Can I share my screen?
Not now.
Oh, okay. All right.
A little bit. Okay. And then explain to you. Then we can start.
All right.
It will be 6 presentations. First one was you. You are invited person, and we are happy to see you here. So we have still 2 minutes. Let me talk
That's
about.
Okay. No problem. No problem.
Okay. How is pandemic in there? Pandemic situation. Pandemic. Yes.
Yeah, it is my first time to Turkey.
Oh,
virtually. Virtually.
Okay. Okay, and we have still 1 minute to start. I think we can start. Professor, can you share the screen? Yes, the bottom of the green one, the share screen.
Yeah, okay, yes.
Did you see? Yes. I think
yeah, okay, yeah, you're right.
You can select the first one, but I want to get permission to explain to you a little bit. Thank you for attention our conference. And Professor Prusitam Jena, he was born in India. Now he has a citizenship from USA, and he is married and he has one son. His education from California University, PhD physics and master and other physics educational from India. So an academic appointments and other significant work experience, highly huge. Thank you. And his experience during his academic career, very nice science follows science and technology, worked with U.S. government interagency team to organize the Washington International Renewable Energy Conferences. And also he has fields of special interest, the condensed metals, alloys, and semiconductors as well. So, and he has many memberships in professional and honor societies. Okay, and also he has many special awards. So let me start, Professor. This is your talk. Have a good luck.
Okay, now how do I...
you can just select the first one as slide share in the bottom of the right side. It's near the magnification in your computer. The right side button.
On the top, I have new...
As far as I see on the bottom sides, the right side, right corner bottom.
Here under more?
Yes, you can just click the slide share from there. Yes, no. Okay, you can also use the home insert draw design. Did you see the upper sides? You can select the slideshow. Yes, you are there. You were there. Slideshow. Please go up and the left side.
Yeah, okay.
Yes, okay. And then yes, left one, the from beginning. The left one. The upper sides from beginning, it's written from beginning.
From beginning. Yes. Okay. Okay. Thank you very much.
You're welcome. Good luck.
Let me see. Okay. Well, thank you very much for inviting me. And I wish I were physically in Turkey rather than in Richmond, Virginia. And hopefully someday I will have a chance to visit you guys. And first of all, let me acknowledge the people with whom I had the pleasure of working. And my current postdoc is Hong Fang, and Rosie Behera was my graduate student, and Santanab Giri was a former postdoc. And the work that I have done is funded by the Department of Energy. Let me start with something that we'll all agree, and that is one of the greatest challenges in the 21st century is to find clean, abundant, renewable, and affordable sources of energy. And of course, those sources are plenty. We have the sun and the wind and the water. But the challenges are that the solar and wind energies are intermittent, and one has to store these energies. And for that, what one needs is very safe solid-state batteries with very fast ion conductivity. And then for water, one needs to produce hydrogen from water. And once you have hydrogen, that needs to be stored. So these are the challenges for the renewable energies. Now, I will mostly talk about lithium-ion batteries, although I have done a lot of work on hydrogen storage, but lately my interests are mostly on batteries. Now, if you look at a traditional battery, it has three components. It has the anode and the cathode, and of course, the electrolyte. There are challenges in all these components of the batteries. For example, for the electrolyte, we need safe solid-state electrolytes that have super-ionic conductivity. For the anodes, we need very high capacity anodes. And for hydrogen economy, the biggest problem is how to store hydrogen in materials with very high gravimetric and volumetric densities, and these materials have reversible hydrogen storage. But as I said in the beginning, my talk will be mostly on solid-state electrolytes in lithium-ion batteries, and I'll focus on two particular classes of electrolytes. One of these is halogen-free electrolyte, and the second kind of battery electrolytes are based upon what we call antiperovskites or argyrodides. And then I will conclude. Now, for the electrolyte lithium-ion batteries, the current one that you are using is organic liquid electrolytes. So here I have listed a few of the commonly used organic electrolytes in lithium-ion batteries. And if you look at this one, these essentially are lithium salts composed of a lithium cation. And then you have a negative ion that is usually very complex. It contains more than one element, but the one that I have marked in red are the negative ions. And if you look at these ones, most of them contain either fluorine or chlorine. And fluorine and chlorine are highly toxic, as well as they are corrosive and they corrode the electrodes. The liquid electrolytes are also highly flammable. So what one needs is to find electrolytes that are not flammable, that are not toxic, and that do not contain halogens. So the desired properties of battery electrolytes from the chemical point of view, they have to be unreactive towards anodes and cathodes. They have to be non-corrosive, either low or not flammable, and non-toxic. From the physical characteristics, they have to be low volatility and very high thermal stability. From the electrochemical point of view, you need large electrochemical stability window and high conductivity. So these are the properties that we need of an electrolyte. Now, what do we need for an electrolyte to have large ionic conductivity? Well, the lithium ions that actually migrate. So what you need is a large channel space for the lithium ion to migrate, lot of room through which they can migrate. They also have to be low activation barrier, so they can overcome. In addition to the large channel space and activation barrier, they have to be thermally, dynamically, and mechanically stable. So our approach to design these electrolytes is what I call bottom up. That means we start with single atoms and we start building these electrolytes. And here I have listed some of the 4 papers that I'm going to use for today's presentation. And if I do not cover things carefully, or you cannot understand my English, please, you can read these papers. If you look at this electrolyte that I showed in the beginning more carefully, as I said, these are complex molecules. For example, you have nitrogen, sulfur, oxygen, fluorine, boron, fluorine, all these things. And if you look at these things carefully and look at their outer valence electrons, you'll find that all these molecules need 1 extra electron to have a closed cell. That is why you have a lithium salt, where lithium is the cation and these are the negative ions. The only difference between, for example, a halogen, which is also electronegative, and these complex negative ions is that here the electron is distributed over a much larger number of atoms. And this is the property that is most important to design these electrolytes. As a matter of fact, these class of molecules, which are large, but they behave like a halogen, we call them superhalogens. This concept was actually given by Gennady Gutsev and Boldyrev in 1981. Imagine they have a metal atom, and this metal atom has a valence 5. So which means you can attach 5 halogens to this metal atom. However, if you add a 6th halogen to it, this halogen would require 1 extra electron to have a closed cell. But when you have the metal atom with 6 halogens and you add 1 extra electron, then the entire molecule have a closed cell. But this extra electron now sees not 1, but 6 negative ions. So therefore, this electron is distributed over a much larger phase space. So when the electron is delocalized, the electron-electron repulsion will decrease, which means the energy that you gain will increase substantially. For example, if you take chlorine and you add 1 electron to chlorine, you will have an electron gain, energy gain of 3.6 eV. This is what's called the electron affinity of chlorine. In the periodic table, chlorine has the maximum electron affinity, 3.6 eV. But in a superhalogen, the electron affinity can be much, much larger, as high as 15 electron volt. So not only the superhalogens have large size, they also have very large electron affinity. Now, if you take all the negative ions that I showed you in the beginning, which are components of the current organic liquid electrolytes, you find that the electron affinity is more than 3.6 eV. They are as low as 4.3 to as high as 7 eV. So which means these negative ions are superhalogens. And if you look at how much energy does it require to dissociate a lithium salt into positive ion and negative ion, these are the energies in the second column, anywhere from 5.8 eV to about 7.4 eV. So you need to dissociate a lithium salt so the lithium ions can actually move. And all these salts are have strong affinity towards water, and the binding energy to water is about 1 electron volt. So these are the properties of the current electrolytes, how much energy you need to dissociate into individual ions, what are the electron affinity of the negative ions, and what are their sensitivity to water. So if I want to find a negative ion that does not contain at all any halogen, then that's what I'm after, an halogen-free electrolyte. Now, actually, about 10 years ago, on a very separate project, I was interested in superhalogens that do not contain a single halogen atom. At that time, I had no interest in electrolytes or batteries. It turns out that what we did 10 years ago happened to be exactly the right negative ion to produce a halogen-free electrolyte. So let me go through this one. This is a classic molecule, inorganic molecule called dodecaborate. It has 12 boron atoms and 12 hydrogen atoms. The 12 boron atoms are arranged in an icosahedric configuration, and the hydrogen atoms are now radially bonded. So this, the negative ion, for example, of a lithium borate, this is readily available, commercially. But if you look at this one, it really requires 2 extra electrons to be stable. Just like chlorine requires 1 extra electron to be stable. Chlorine is highly reactive. Once you add an electron, it becomes chlorine minus, and that is more chemically inert, just like your noble gases are because of closed cell. Now, this particular B12H12 needs 2 extra electrons to be stabilized. Now, imagine that you replace one of the boron by carbon. Carbon has 1 extra electron than boron has. So a new molecule that has 1 carbon, 11 boron, and 12 hydrogen, they only need 1 extra electron to be stable. Just like chlorine need 1 extra electron to be stable. This particular anion is called carborane. This is also commercially available. The question 10 years ago you asked, is carborane a superhalogen? Because this negative electron is distributed over the entire cage of this molecule or cluster. So we calculate the electron affinity by finding out the energy of the negative ion and energy of the neutral and taking the difference. And that is 6 electron volt. Recall that chlorine has an electron affinity of 3.6 eV. So this particular negative ion is not only much bigger than chlorine, but it also has a very large electron affinity. This particular quantity is important for electrolyte because larger is the electron affinity of the negative ion of the salt, your larger will be the electrochemical window. That means the battery can operate over a much larger voltage, which is required. So this particular carborane does not contain a single halogen atom, yet it behaves just like chemically like a halogen. So then the question was, can this be the negative ion component of a new lithium electrolyte? So then we calculated, as I said, the electron affinity, which is 6 eV. So that is a super halogen like any other negative ion of electrolytes is satisfied. The energy to dissociate a lithium carborane salt into lithium ion and your carbon negative ion is 5 eV. It is less energy to dissociate than any other electrolyte that is known. Its affinity to water is 1 eV, just like any other electrolyte. So that means this lithium carborane should be a very good electrolyte for halogen-free electrolytes for lithium-ion batteries, much better than any other electrolyte that is known. That was the prediction that we made in 2014. Within a year of that prediction, there were 2 experiments, one at the Toyota laboratories in Dearborn, Michigan, in the United States, and the other one by Professor Orimo at Tohoku University in Japan. The scientists at Toyota tried to see if this carborane can be used for magnesium batteries. There were no known good electrolytes for magnesium batteries. And when the Toyota group did the experiment, this is what they found. This achievement is a turning point in the research and development of magnesium electrolytes that has deep implications on realizing practical rechargeable magnesium batteries. Our prediction was, of course, for lithium, and this group found that that is also very good for the magnesium batteries. The Japanese group used this particular negative ion for lithium and sodium ion batteries. And what they found is that this is truly stellar ionic conductivity that surpasses any known polycrystalline material. So we are very happy that ultimately what we predicted to be a halogen electrolyte indeed is practically feasible. So that has changed now a paradigm shift in using density functional theory to predict electrolytes for lithium-ion batteries. The second group that we are interested in is what I call all solid state batteries. Now, as I said, the electrolyte is liquid, and this particular liquid electrolytes, they corrode the anodes and the cathodes, and they are highly flammable. So to not only make the batteries more safe, but also to increase their efficiency, what one needs is to go to a solid, all solid state electrolyte, which will not be flammable. Of course, the problem with the solid electrolytes is that the conductivity is very low. Ions can move much faster in a liquid than they can move in a solid. The advantage, of course, it is greater safety and higher energy density. In the organic liquid, the advantage is a very high conductivity, but they're reactive, corrosive, flammable, toxic, and low density. So there are 2 classes of materials that people are using now. One is called anti-perovskites, and the other one is argyrodides. There is a spelling mistake here. So let me show you what a perovskite looks like. These perovskites are cubic. These are again salts. These are three components. You have the A site like cesium, B site like lead, and X sites like iodine. Here is your A, B, and X. These are cubic systems. So cesium lead iodide is a typical perovskite. In an anti-perovskite, what happens is that you simply exchange your cation to anion and anion to cation. So lithium 3OCl is then an anti-perovskite, where your lithium 3O becomes the cation, and then chlorine becomes the anion. So in a perovskite, the metal cesium is the cation, but in the anti-perovskite, lithium 3O becomes the cation. So here in the perovskite, the complex molecule is the negative ion. In the anti-perovskite, the complex molecule is the lithium 3O ion. That's the difference between the perovskite and anti-perovskite. So these are the crystal structures of these two compounds. So as I said in the beginning, to get a high ionic conductivity, you need large channel space for lithium ion to migrate. So if you replace chlorine by something like, say, BH4 or BF4, these two behave exactly like chlorine, except that the size is bigger. So when you replace some of the chlorine by BH4, you have more space around the chlorine for lithium ion to migrate. So, but the chemistry is still the same. Both BH4 and BF4, they mimic the chemistry of chlorine. So these again are superhalogens. Now, what are the advantages? Why do we need to replace chlorine with BH4 or BF4? Well, as I said, these are bigger in size. So therefore, larger the size, larger is the channel space for lithium ion to migrate, and therefore the conductivity will go large. These are superhalogens, meaning that electron affinities are larger than that of chlorine. So you have a large electron affinity, then you will have a large band gap. If you have a large band gap, you will have large electrochemical window, which means the battery can operate over a larger voltage. The third and equally important is that the symmetry. This BH4 or BF4 are clusters in which you have boron at the center with 4 hydrogen or 4 fluorine forming a tetrahedron. So chlorine as a negative ion has spherical symmetry. But BH4 or BF4, even the carborane which I showed you before, do not have spherical symmetry. These ones have tetrahedral symmetry. So which means at low temperature, when these halogens or superhalogens begin to rotate, then that is going to influence the energy landscape around it. And this rotational degree of freedom invariably lowers the activation barrier. So by replacing a spherical halogen by a non-spherical superhalogen, you achieve 3 things: the large channel space for lithium ion to migrate, the large electron affinity that gives you large electrochemical window, and then the non-spherical symmetry, which lowers the activation barrier. So these are the 3 characteristics. So here I'm going to show you. So this is lithium 3OBF4. You can also replace oxygen with sulfur. You can replace fluorine with hydrogen, for example. So there are many systems of salts of these perovskites or anti-perovskites that you can design, not based upon atoms, but based upon molecules or clusters as building block. So once we replace chlorine, say with a superhalogen like BF4, then we need to find out what the crystal structure will be and will their crystal structure be stable. So this is where we do density functional calculation, in which we determine the equilibrium geometry of a crystal that contains 3 lithium, 1 oxygen, 1 boron, and 4 chlorine. And we calculate the density of states, the electronic band structure, the band gaps, and more importantly, whether or not it is dynamically stable. So we calculate the phonon frequency of the optimized geometry of this superhalogen containing antiperovskite and find that all the frequencies are positive. That means that this particular material is dynamically stable. Once we understand the dynamical stability, then we can actually do the I do not know why this thing does not work.
Okay, we have just 2 minutes to complete.
Oh, 2 minutes. Okay. Well, this molecular dynamics, if it worked, will show you that actually this tetrahedra they actually rotate, and once they rotate, then the lithium ions can migrate. So here are the properties of this new perovskite, antiperovskite. It is thermally has very low thermal expansion. It is stable up to 600 degrees Kelvin. It has room temperature conductivity that is equal to the currently liquid liquid electrolytes. Its band gap is more than anything that is ever known, 8.5 eV. It has a very low activation barrier. Now, if you replace some of the superhalogens with, say, chlorine, you have a mixed phase, then you can even increase the conductivity by another order of magnitude. Since my time is not there, this is a way in which one can actually synthesize this particular one. So I'm going to close by summarizing that the components of electrolytes of lithium-ion batteries can be designed from the knowledge of cluster science. The band gaps can be tailored by using the concept of clusters as superatoms. And most important, that the cluster science that developed over last 50 years with no relevance to really material science. But the knowledge that we gained from cluster science can actually be used to make advances in real materials. So I'm going to end with a quote that I very much like. A friend of mine, Russell Grimes, once said that chemistry, like other branches of science, is most exciting when it's expanding into uncharted territory. I hope I have shown you that how we can use knowledge from one field of science to be an entirely different field, which initially had no relevance, and yet be able to come up with materials that are far better, and indeed experiments can actually validate those theoretical calculations and actually produce a current battery. So right now, there are many groups around the world who are trying to design or synthesize the electrolytes that we have predicted. And I'm waiting for them to actually sell these batteries so I can make money. Thank you very much.
Okay, thank you, Professor Jena, because it was very wonderful presentation. Thank you for attending our conference. And I want to ask to participants, do you have any questions to ask to Professor Jena? If it's not, I will continue. Do you have any questions to Professor Jena?
No, but you can always email me. I know English is a problem. You have my email address. It's pjena@vcu.edu. I should have written that. And you can email me, or perhaps there is a channel through the website that you can ask me questions as well. But
Okay.
I'm happy to answer now if you like.
We are happy to see you here. Thank you so much. Now we can stop here and then we can continue with the second presenter. Thank you so much again. See you.
Okay. Thank you. Thank
Okay.
you.
Thank you. Bye.
Bye.
And now in the program, we will, let me see, yes, the hydrogen storage characteristics of perovskite type hydrides. Gökhan Sürücü, Middle East Technical University, and Ayşenur Gencer from Kahramanolu Mehmet Bey University. Hello, Ayşenur. Welcome to our conference.
Hi, Professor Molkoç.
Okay. Let me start, and here you are.
Okay, I share my presentation. Could you see?
Yes, we can see. You can start.
Okay, thank you, Professor Molkoç. I am Dr. Ayşenur Gencer, and I am a research assistant at the Kahramanolu Mehmet Bey University. And today our presentation title is Hydrogen Storage Characteristics of Peroxide Type Hydrides. This is the presentation outline. I will start with the hydrogen storage techniques, and I will move on to our studies on the perovskite type hydrides. That includes three groups of materials. One is the calcium X hydrogen 3, and the other is sodium X hydrogen 3, and the last one is X nickel hydrogen 3. And then I will conclude my presentation. In everyday life, we use laptops, cell phones, other electrical devices, and portable energy sources is necessary. Also for the leisure activities and military applications, we need portable energy sources. And currently, we use batteries for these portable energy sources, but batteries has limitations, and fuel cells is one of the promising solutions for the portable energy sources, and hydrogen fuel cells is one of these fuel cells, because hydrogen is the most abundant element in the world, and it is environmentally friendly power source, because when we combust hydrogen, we get water as a byproduct. And we need to store hydrogen for these techniques. And the hydrogen storage techniques is divided into three: gas hydrogen storage, liquid hydrogen storage, and solid state hydrogen storage. At ambient condition, hydrogen is a gas, and we need high pressure vessels to store hydrogen as a gas. And for this method, the safety is important. We need to take the safety precautions. And for the liquid hydrogen storage, we need to liquefy the hydrogen, and therefore we need extra energy, and the boiling of hydrogen is another issue for this method. We need to consider the boiling of hydrogen. For the solid state hydrogen storage method, we could have physically bound hydrogen or the chemical bound hydrogen method. And for the physical bound hydrogen method, the hydrogen atoms bound on a surface, material surface, and the high surface area carbon nanotips are generally used. And for this method, we need to have low temperatures, because there is no van der Waals force between the hydrogen atoms and the surface. And for the chemically bound hydrogen method, the hydrogen atoms make bonds between the materials, and complex hydrides and metal hydrides are used. And we need the high temperatures to release the hydrogen for the chemically bound hydrogen systems. And therefore, each method has advantages and disadvantages. And US Department of Targets set targets for the portable power equipment, and these are some of these targets. For example, we need the gravimetric hydrogen storage capacity as 4.8% for single-use portable power equipment, and 3.48% for rechargeable power equipment. Also, these are the targets for the volumetric hydrogen storage capacity, and we need to have these portable power equipment operated at ambient temperature between -40 degrees Celsius and 50 degrees Celsius. And there is also a requirement for the pressure at the coast. And as you can see, the gravimetric storage capacity is important, and it is the amount of hydrogen stored per unit mass of a material. And we can obtain this storage capacity using this formula. And another important parameter is the hydrogen disruption temperature. It is the required temperature to release the hydrogen. And we can use these one-off equation, and if we take the P, the composition temperature, as a 1 bar, we get this equation. If we know the reaction enthalpy and the entropy change, we can calculate the disruption temperature. And for the hydrogen storage systems, the entropy change comes from the hydrogen atoms. It goes from gas phase to solid phase or vice versa. And this entropy change is given here. Then if we know the reaction enthalpy, we get the disruption temperature. And as Professor Jena introduced us the peroxide materials, they are a special group of materials, and they have, for example, hardness and ceramic nature, and this is the crystal structure. The ideal crystal structure is cubic. However, we can find that the distorted structures as orthorhombic or hexagonal. And if we change the X atom here in the peroxide type materials as hydrogen, we get the peroxide type hydrides with the ABH3 formula. In this study, we consider peroxide type hydrides using the density functional theory calculations. And in the morning section, we listen lots of presentations using density functional theory. However, I briefly introduce what is density functional theory. Here you can see the Schrödinger equation, and the solution of the Schrödinger equation is not easy for the many-body systems. This is the many-body Hamiltonian, and sorry. There is lots of interactions between the electrons and the nuclei. And at this stage, we could use density functional theory because density functional theory uses electron density and solve the quantum equations. How we perform density functional theory calculations? Density functional theory calculations are self-consistent. First, we make an initial guess for the electron density, then we calculate the effective potential, then we solve the quantum equations, then we obtain the electron density. If the initial guess and the calculated density is consistent, we get our outputs. If it is not consistent, we turn back to the first stage. And we perform these calculations using several softwares such as CASTEP, WASP, Siesta, and in this study we use WASP. And in the DFT calculations, you can have several implementations given here for the exchange correlation or the wave functions. WASP could have these implementations in the calculations. Let's move on to our results. Our first material group is calcium X hydrogen 3. This is the crystal structure of this material, and these are our calculation parameters. First, we optimized our materials, and we found their lattice parameters. Here you can see that when we change the X atom from manganese to cobalt, the lattice parameter is decreases. And another important parameter is the formation energy. We use this formula given here to calculate the formation energy. And the negative value for the formation energy is crucial because this means that these materials are energetically stable and synthesizable. And here you can see that all these compounds are energetically stable and synthesizable. Then we calculate the gravimetric hydrogen storage capacities, and the highest capacities belongs to the calcium, manganese, and hydrogen 3. Then we move on to the electronic properties. Here you can see the bond structures for these materials, and all these materials have metallic character. And in the right panels, here you can see the density of states, and the most contributions to the density of states comes from the X atom, here for the manganese, here for the iron, and here for the cobalt. And then we obtain the electron density distribution for the calcium, manganese, hydrogen 3, and you can see that the dominant bonding is the ionic bonding. These are the Bader partial charges, and calcium and X atoms has the positive Bader charge. This means that the charge is transferred away from these atoms, and hydrogen atoms has negative Bader charge. This means that the charge is transferred to the hydrogen atoms. After these electron considerations, we consider the mechanical properties. First, we calculate the elastic constants for the cubic structures required. The required constants is the C11, C12, and C44. And for a mechanical stable material, the bar stability criteria should be satisfied. These materials satisfy these criteria. And we use these constants to calculate the mechanical properties such as bulk modulus, shear modulus, Young modulus, Poisson's ratio, G over B ratio, and B over G ratio. Here you can see that the highest bulk modulus, Young modulus, and shear modulus is belong to the calcium, cobalt, hydrogen 3. And the Poisson's ratio could be used to determine the bonding type of a material. If it is around 0.25, the material has ionic bonding, and if it is around 0.1, it is covalent. We can use also G over B ratio for the same purpose. This time we have these parameters here. When we checked Poisson's ratio and G over B ratio, we found that these materials have dominantly ionic bonding. And the last parameter here is the B over G ratio, and 1.75 is important. If the B over G ratio higher than 1.75, the material is ductile, and if it is lower than 1.75, the material is brittle. These materials having lower than 1.75 is brittle materials. Now let's move on to the vibrational properties. These are the phonon dispersion curves for this material. In this plot, there is no negative frequency. Therefore, these materials are dynamically stable. And in the right panels here, you can see the phonon density of states. And the hydrogen atoms gives more contributions to the higher frequencies due to the lighter mass among these materials. Now let's move on to the sodium X hydrogen 3. This is the crystal structure. These are the calculation parameters, and these are the results from the optimization. Similar to the calcium X hydrogen 3, the lattice parameter is decreases when we move to the cobalt atom. All these materials have negative formation energies, therefore they are energetically stable and synthesizable. These are the gravimetric capacities. The highest capacity belongs to the sodium manganese hydrogen 3. And we obtain their electronic properties. They have metallic character. Again, the most contributions comes from the X atoms. And this is the electron density distribution. It has ionic bonding, and these are the Bader partial charges. Sodium and X atoms transfer charge away, and hydrogen atoms get charge. Now let's move on to the mechanical properties. Calculated elastic constants here satisfy the bar stability criteria, therefore they are mechanically stable. And these are the mechanical properties. The highest bulk modulus, Young's modulus, shear modulus belongs to the sodium, cobalt, hydrogen 3. And all these materials have ionic bonding and brittle nature. I think I have out of my time.
Yes.
Okay, I will fastly conclude my presentation.
Please, in 1 minute.
Okay, thank you. Also, we found that these materials are dynamically stable, and my last material group is X-nickel hydrogen 3. For this material, we have experimental results for the lithium nickel hydrogen 3, and our result is consistent. The highest capacity belongs to the lithium nickel hydrogen 3, and the lowest desorption temperature belongs to the sodium nickel hydrogen 3. We obtain their electronic properties. They have metallic character. We obtain also their Bader charges. These are their mechanical properties. They are mechanically stable. Also, they are dynamically stable. These are the thermodynamic properties for these material groups. And let's conclude my presentation. In this study, we consider peroxide type hydrides. They are both energetically, mechanically, and dynamically stable. And the highest capacity we obtain for the lithium nickel hydrogen 3 is 4.48%. And for the lowest desorption temperature, we obtain 447.1 Kelvin for the potassium nickel hydrogen 3. These are all I want to present today. Thank you for your attention, and I will be happy to answer your questions.
Okay. Thank you so much, Ayşenur. Do you have any questions? I can get only one question to ask the Ayşenur. Dr. Gencer, yes. Do you have any questions? No? Okay. But Ayşenur, I want to just tell something that to you because I was very impressed with your presentation. Thank you. The subject is good and also you explained very clearly. Thank you so much to attend this conference. Thank you.
Thank you.
Okay, the next presenter now, the next one, let me look. The structural and electronic properties of lithium aluminum hydrure used as hydrogen storage material. Who will, yes, Dr. Abdul Kayyum Doğan Yaşar Cihan Kürkçü from Kırşehir Ahi Evran University, right?
Yes, yes.
Okay, welcome to our conference, Abdul.
Welcome. Thank you so much for inviting me here also.
You're welcome. And can you share your presentation with us? You can just use share screen.
Yeah, I just, okay.
Green one. Okay. Now I can.
Yes. Now, can you see my presentation here?
Yes, I see.
Okay.
Can you please share with us as a slideshow? Yes, slideshow. The next one. The
Yes.
other slide. Yes.
Okay.
From beginning. Thank you. Now you can present.
Okay. Thank you so much. First of all, my name is Abdul Qayyum and I am from Pakistan. I am doing master in physics in Kırşehir Evran University. So today my topic is structural and electronic properties of Li-AlH4 used as hydrogen storage material. And I am working with my honorable supervisor. They are I have given the name Doğan Yaşar and Cihan Kürkçü. So I will start with my abstract here. The structural and electronic properties of Li-LH4, which is used in hydrogen storage under high pressure, were calculated with the CESTA package program using the ab initio method. Li-AlH4 crystallizes in monoclinic structure with a space group of P21 under ambient condition. When gradually increasing pressure was applied on this structure, a phase transformation into another monoclinic structure with a space group of P1 was obtained. In addition, total energy and enthalpy calculations were made in order to obtain transition pressure values that were more compatible with the experimental results. As a result of these calculations, it was observed that the transition pressure from P21 to P1 phase was about 4.2 gigapascal. In addition, the electronic properties of Li-AlH4 were examined by the effect of pressure. Gravimetric hydrogen density, a key parameter for Li-AlH4 to be used as a hydrogen storage material, was also calculated. So here the gravimetric hydrogen density we have calculated is 10.62% of the weight. So here is the introduction. Ternary aluminum hydride could be an extremely efficient energy storage system owing to their high gravimetric and volumetric hydrogen densities. Of these, Li-AlH4 is prominent hydrogen storage material with 10.8% of the weight, theoretical hydrogen content, and thus has recently received much attention. Besides, because of decomposing at moderate condition, it is regarded as a practical hydrogen storage material. The application of pressure can induce significant changes in atomic and electronic structure, which allows tuning the atomic structure and probing the nature of chemical bonds to produce novel morphism. In the last decade, remarkable progress in studying high pressure behavior of Li-AlH4 has been aroused by a new predicted high pressure structure. Before that, Vagistan et al. Predicted a transformation from ambient structure to a tetragonal phase with a space group of I41A with a large volume collapse greater than 17% at about 2.6 gigapascal. So they proposed that it would be interesting to study the reversibility and stabilization of high pressure phases, which have been predicted to exhibit superior hydrogen storage characteristics. If such a large volume collapse can be determined experimentally and the high pressure phase can be retained at ambient pressure, this will lead to new dense hydrogen storage material with gravimetric as well as volumetric efficiency. However, the crystal structure as the key to understand the intriguing high pressure behavior of LiALH4 remained elusive for several decades. So in my work, we have these methods and computation. In our work, our calculation were carried out by using a initial program that is called Siesta program. So we have used the first principal calculation with the density functional theory method. The exchange correlation energy was calculated by the using generalized gradient approximation GGA. We have two exchange correlation energy LDA and GGA, but we have selected here generalized gradient approximation of Perdue, Burke, and Zorn. A cutoff energy of 250 Rayleigh was used in all calculations in my work. The simulation cell consisted of 96 atoms with periodic boundary conditions. The Brilliant zone integration was performed with 865 and 864 K-point meshes for P21 mean monoclinic and P1 trigonal phases of LiALH4 respectively. These K-point meshes were utilized for the energy volume calculations. So conjugate gradient technique was also used to apply external pressure to the system. Pressure was then increased with a increment of 5.0 GPa gigapascal. In order to analyze each minimization step, the K-plot program was used to use, which gives elaborated knowledge about latest parameters, atomic positions, and space group of an analyzed structure. Now, if we talk about the result and discussions, the calculation of equilibrium lattice parameter of the monoclinic P21 phase lattice parameter as I have given here. A is 5.0627 angstrom and B is 7.5699 angstrom. C is 7.957 angstrom, and here alpha gamma are equal to 90 degree and beta is equal to 110.7225 degree of LiALH4 were performed initially by relaxing 96 atoms supercell at zero pressure. In order to determine the phase transition of LiALH4, the pressure volume relation is obtained by using the constant pressure ab initio simulation. So the PV curve as I have given in this figure 1, a sharp change is observed in a volume as the pressure increases to 10 gigapascal. You can also see this on this graph. As you see, after 5 gigapascal, there is a sharp change is observed in a volume to at 10 gigapascal. So this indicates that a first order pressure induced phase transition have been observed in LiALH4. So if we talk about the structural properties of this LiALH4, okay, if we talk about structural properties of crystal structure of this LiALH4 transformed to trigonal shape, and this lattice parameter here we have different angles. The angles are totally different. Alpha, beta, and gamma are also different, and the lattice parameter A, B, and C are also different. Here you can also see that A is 4.3702 angstrom, B is 5.5890 angstrom, C is 6.3317 angstrom. Alpha, beta, and gamma angles are also different at 10 GPa pressure, as shown in figure also too. Here you can see that first of all we have a monoclinic structure of LiALH4. After after we have applied the percent pressure at 10 GPa, we have a trigonal phase of the LH4. Here the results suggest that the successfully generate phase transition of LH4 at high pressure. However, the calculated phase transition pressure is slightly higher than the experimental values. This is due to using a defect-free structure with a finite volume where the phase transition occurs over the whole simulation cell instead of nucleation and build-up. Thus, when this particular condition such as the finite size of simulation cell, the time scale of simulation etc. are considered, such as overestimated transition pressure is anticipated. In order to avoid this situation, energy volume calculations are considered to study the stability of monoclinic and trigonal structure, since the thermodynamic theorem does not take into the account the possible existence of such activation energy barrier separating the two structural phases. Result is also shown in this graph. There is a energy volume curves of structural phases of LH4 as you can see from the graph. So by using the values of energy volume values, we can also use the you can also calculate the Murnaghan equation of the state. In that phase transition, the two phases have the same enthalpy. H is equal to as given E dot plus PV, where PV is equal to minus DET dot over dV is obtained by direct differentiation of calculated energy volume curve. Therefore, the transition pressure can be easily determined by the equating the enthalpy of two phases. The computed enthalpy curve of the monoclinic and trigonal structure, as also you can see from this graph here, the enthalpy curve of structure phase in energy Murnaghan equation is also given 4.2 gigapascal. So if we come to the electronic properties of LH4, we calculated the electronic band structure of LH4 along the high symmetry direction and illustrated near the Fermi energy level as a function of energy as shown in this figure. Fermi level was set to be 0 electron volt. The EBS of LH4 demonstrates that the valence band is located below the Fermi level, where the conduction band is located above it. The monoclinic phase of LH4 corresponds to direct band transition with a band group of about 4.40 electron volt due to the valence band maximum and the conduction and minima lie on the same symmetry. They are also lying on the same symmetry point are gamma and gamma. Thus, P21 C phases of LH4 shows semiconductor properties here in this figure. In figure 5, we displayed that conduction bands seem to cross each other. You can see from this figure that in this figure, conduction bands are crossing each other. So we can suggesting that LH4 is conducting material in this P1 phase and show metallic behavior. In monoclinic structure of the LH4, it was showing the semiconductor behavior, but in after changing into more trigonal phase, it shows metallic behavior here. So total density of the also we have the monoclinic and trigonal phases respect, as we can see from the figure that the largest contribution came from the hydrogen, as you can see from the here below the below the energy level, highest contribution came from the hydrogen, and above the Fermi energy level, although the largest contribution in the 0 to 8 electron volt range from it comes from Al, as you can see in this figure. It comes from, and from 8 to 9 it shows some changes, and it comes from lithium and it is from 8 to 9 electron volt. Okay, so at the last we concluded that we have performed an Ibisho constant pressure technique in order to study the pressure and transformation in the monoclinic structure LH4. A first order phase transformation from monoclinic to trigonal structure is productively perceived through these simulations. Furthermore, we study this phase transformation of DLH4 via the total energy and the enthalpy calculations. In addition, we have plotted the electronic band structure and the density of state from monoclinic and trigonal phases of LH4. Thank you. My seminar was.
Okay.
Yes. Thank you so much for listening me.
Thank you, Abdul. And do you have any questions to ask to Abdul, Qayyum, or I will ask? Is it possible? Can I ask Abdul?
Yeah, you can ask.
Okay. Can you show me the figure 5A? Because I saw a strange things in the figure. I didn't get it. What was that? Because I haven't seen a brilliant zones of the electronic structure, and it was a little bit complex in figure 5A.
Yes.
I just haven't get, maybe some explanation is enough for me. Figure 5E, it was an electronic structure, I think. Yes. Yes, in here.
Yes.
I haven't get the brilliant high symmetry points. Why you select gamma Y, and I haven't seen. Yes, maybe it's better to see bigger.
Yes.
Okay, in here, yes, you used Z, X, and A, gamma Y. It's the mono. It was a monoclinic, right?
Yes.
Yes. Okay. And I didn't get these high symmetry points by you choose as the Z and X. Did you determine by yourself, or?
Yeah, it was actually we have calculated from the simulations. We have used the simulation. From simulation we have calculated this.
West, right?
Yeah.
West. Okay, I didn't get why you used this. Why didn't you choose the same point for Z and X? Because it's not continuous and it looks mixed for me. I want to just ask this question, and that's all.
In this figure, you can see that there is a band structure here. So
yes.
The last point, there is a minima and the maximuma. The bottom one is the I think it is the valence bond, and it is lie on the same symmetry also, gamma and gamma. So here there is a actually band structure, band gap here. So we can say that we have a semiconductor properties from here.
Yes, I got this point. I just ask the high symmetry points. Why you use select Z and X for it's the same point to. I haven't seen a continuous spectrum. Just I asked this, but it doesn't matter. I will search. Okay. Thank you so much, Abdul.
Yes, I got your question. Actually, as I have said to you that we have calculated it from the simulation, so it automatically gives this result.
Oh, okay. Okay, I wonder that one.
Yes, automatically it is giving this result. We cannot say it is because it is not experimentally calculated.
Okay. You didn't determine by yourself. You use software.
No. We have calculated from the simulation, so it automatically gives this answer.
Okay. This is monoclinic structure, and you can use these high symmetry points.
Yes,
okay. Yes. Thank you so much again.
Yeah. Thank you so much again from
okay.
me. Okay.
Let me stop your presentation to stop share for us. Thanks. And the next presenter, okay. The next presenter, Derya Öncel, Özgür, and Yasemin Çiftçi. They're from Gazi University. They will attend from Gazi University. And the title is Hydrogen Adsorption on Lithium Decorated Molybden Disulfide, a DFT study. I'm very excited to listen this because I know Derya. Hello.
Hello, Yeşim.
Hello.
Actually, I prepared a video. I'm not sure who share. Actually, if me, I can share my video.
Yes, okay. You can share by your screen, and then you can just open your video. I think we can.
Okay.
So sorry, I am a technical staff, and I can share the video.
My video. Okay, no problem. I can share my video. There's no problem.
Yes, see you.
Okay.
Thank you. but there is no voice. Yes. Maybe we can get some help from Professor Aydın. Yes. Daria, can you stop your presentation because it doesn't work now? Okay. Let me wait for help.
Okay. I see what's the problem. I closed my voice and now
Yes.
open. I think there's no problem.
Okay, let me see.
Okay. Good evening, everyone. Let me introduce myself first. My name is Derya Öncel Özgür from Gazi University at Chemical Engineering Department. Today, I would like to present the topics hydrogen absorption on lithium, molybdenum disulfide, ADFD study. Here is our presentation contents. Firstly, I would like to talk about the energy, especially the hydrogen energy, and then the theoretical background, the calculation methods, computational process. Lastly, I give in the results and discussions. As you know, fossil fuels is one of the major energy resources being widely used to meet our energy requirements. But there are some serious problems with using fossil fuels. Many consider that it is the major source of the global warming, and other best known problem, this resource is depleting fast. The solution to the problems of limited fossil fuels and their impact on the environment is to have renewable resources play a larger role in the supply of energy. Converting sunlight, Earth's heat, and nuclear power into energy could, in the next century, meet most of the world's energy needs. Although renewable sources that have environmental benefits is superior to the fossil fuels, renewable sources have some limitation in the energy demands because it have new and developing technologies and the discrete energy supply. It's clear that if the hydrogen energy system replies in the all area, those problems can be solved. Hydrogen is not a primary energy resource, it's an energy carrier. Therefore, it can be transport energy from one way to another way and used as a fuel. Hydrogen can be produced from fuels and from renewable resources in a clean way. The interest in hydrogen as energy of the future is due to the being a clean energy, most abundant element in the universe, in lightest fuel, richest in energy per unit mass, other kind of the properties also, so it can be easily stored. So studies on hydrogen energy are increasing day by day. We can categorize all studies mainly in three parts: hydrogen resources, hydrogen production methods, and hydrogen storage. Hydrogen storage plays a vital role in the advancement of the fuel cell. This is the application area of the hydrogen storage materials. And hydrogen technologies, the critical for the future success of the overall hydrogen economy. One of the important problems related to hydrogen energy is the improvement of appropriate hydrogen storing materials and enablement of use in practice, use in fuel cell technologies. As a result, attention has been focused on the design and operation of compact and efficient devices designed to generate hydrogen on board vehicles. As a result, we prefer to study the hydrogen storage materials, and we studied the hydrogen storage properties of the molybdenum disulfide in terms of theoretical approach. And for using this theoretical approach, we're using this kind of theories and the functionals. All calculations are carried out using density functional theory and implemented the Material Studio and the MOL package. We adopt the local density approximation to perform the electronic exchange and correlation effects. Molybdenum disulfide sheets contract as 4x4 supercell and 32 sulfur and 16 molybdenum and one decorated atoms. One decorated atoms as we prefer the lithium atoms. The geometry relaxation is executed until the force on each atom is less than 0.002 Hartree angstrom, and 3 by 3 by 1 K-point set is used for the chosen supercell with a 20 angstrom vacuum. In the literature, we can see the graphene and the graphene-based materials to be used in hydrogen storage. However, still far away from the target in terms of hydrogen absorption value. This is the target hydrogen absorption energy value between the 0.2 and the 0.6 eV. But if you look at the graphene-based materials, it's theoretically evaluated the absorption energy value range between 0.1 and the 0.9 eV. So try to increase these numbers, but especially for storing hydrogen, materials should be lightweight, and the absorption energies of hydrogen molecules should remain between physisorption and the chemisorption energy range, neither too strong nor too weak, so that reversible absorption and desorption should take place in the ambient conditions. So our purpose is to investigate the absorption properties of molybdenum disulfide materials, differ from the graphene-based materials. To the best of our knowledge, there have been a few DFT studies related to this kind of materials. We aim to investigate the interaction between the hydrogen and lithium decorated monolayer of molybdenum disulfide by DFT studies. In the literature, studies have shown that by decorating surface with alkaline earth metal, particularly calcium and the lithium, has larger effects on the absorption energies. Incorporation of such kind of metals on such structures makes them active for hydrogen absorption due to their lower weight and the lower cohesive energies, which makes avoid the clustering and hence could help in achieving higher storage capacities of the hydrogen. In this study, we preferred the lithium as decorating atom on the molybdenum disulfide. A systematic theoretical study of the structure was performed. Besides, absorption energy and absorption configurations of gas molecules were also analyzed. Hydrogen absorption is investigated where lithium atom behaves as a primary hydrogen sources and the molybdenum disulfide monolayer as secondary hydrogen sources. We first studied the structural properties of the pristine molybdenum disulfide monolayer. Here we are seeing the optimized structure with top and the view side. And here we are also seeing that the optimized the lattice parameters as A and B, C. This found number is which is good consistent with previous reported work by experimentally as well as the theoretically. After the optimized the molybdenum disulfide structures, and then we consider the lithium atom absorption on the pristine molybdenum disulfide layer. Firstly, we search the favorable binding sites of the lithium molecules by placing it at different possible sites, including the top site of the sulfur atom, the top site of the molybdenum atom, and the hollow center in hexagonal rings. The most stable absorption site of the lithium atoms, if you look at these final energy values, the top site of the molybdenum atoms is the stable absorption sites because when comparing the final energy values. Here we are seeing to optimize the lithium atoms on the molybdenum disulfide surface. The average binding energies the average binding energies of the lithium is determined by using this equation and find as 1.9 eV. After the decoration of the lithium atoms, we investigate the absorption behavior of the hydrogen molecules on the lithium decorated molybdenum disulfide surface. The average absorption energy of hydrogen to the system is defined as the given equation. Firstly, a single hydrogen molecule is attached to the lithium atoms. The distance between the hydrogen and the lithiums are little than the 2.6 angstrom. To determine the hydrogen storage capacity of lithium molybdenum disulfide, the hydrogen molecules are attached one by one to lithium atoms and relaxing all structures. The relaxed hydrogen storage system based on the hydrogen absorption on lithium molybdenum disulfide with different number of hydrogen are given in the table. It's turned out that a single lithium atom on the molybdenum disulfide sheets can absorb up 7 hydrogen molecules, like the 7. Here we are seeing some pictures related to hydrogen absorption onto monolayer and bonding between the lithium and the hydrogen molecules. Lastly, we examine the electronic bond structure and density of states for proposed structures. It's well known that the bulk molybdenum disulfide is semiconducting materials. The strategy of insertion of add atoms, here is the lithium, has enhanced the electronic conductivity used farther area, not only the absorption materials. Maybe we prefer the use of this kind of materials, the locked electrode materials and the locked electronic materials. So lithium insertion results the change in the semiconducting behavior of the molybdenum disulfide and shifting it to a metallic nanocomposites materials.
Okay,
in summary, we have investigated the hydrogen storage behavior of the lithium decorated molybdenum disulfide sheets using first principle calculations. It's found that the absorption of the hydrogen molecule on the pristine molybdenum disulfides is too weak. However, lithium decoration on it can improve significantly the absorption energy to the desired energy range. Thank you for your attention.
Thank you, Daria. It was very nice, but I haven't heard you. Sorry, maybe your microphone is not working now.
You're welcome.
Okay, it was very nice study. Just do you have any questions? I should ask. Do you have any questions from the participants? If there is no, I have one more question for you.
Okay.
It was really, I was really excited when I listened this study because it's very related with me. It's the 2D materials. It's my site. And my question is, your total energy values are very high, and maybe you should check. There is something going wrong because the energy values are too big, and it's like you need to control it, please, because your total values are very huge. And okay, your binding energy is okay because we are getting the differences of them. Maybe there is a problem with your total energy. It's not an EV. You should check, please. You should check, or can you show me?
I think if I remember correct, the heart rate, not the EV.
Yes, but now in presentation, it was in EV and it was very high if it's in EV, okay?
I'm sorry, I remember if I correct, this is the heart rate, not EV.
Okay. No, it's okay. No, I have no question.
Okay.
Thank you so much. It was very nice. Thank you.
You're welcome.
And okay, see you. And the next presenter, Büşra Çal Hacı Özışık from Aksaray University. Hello, Büşra, are you here? Büşra Çal. Büşra studied the physical properties of calcium, magnesium, zinc, and calcium zirconium zinc nanocrystals, right?
Yes.
Okay. Can you share your presentation with us?
Dear Chair, so sorry. The speaker is joining with a video.
Good afternoon, everybody. I am Büşra Çal and a master student at Aksaray University. I am going to talk about two zinc-chloride compounds and their physical properties, which is a part of my master thesis that we have done with Associate Professor Dr. Hacı Özışık. I will talk about what's my motivation in this research and then the methods we used in the study. Next, I will share results and discussions that are obtained about structural, mechanical, and electronic properties and anisotropy. Finally, I'll summarize our study. And alloys of magnesium element, known for their high strength and hardness for their weight, have been used in automotive aerospace studies for years. Additionally, calcium, magnesium, zinc, and strontium and zinc are important for human body, which synthesize DNA, help us heal and support our immunity. It's also used in implants as biodegradable materials. These are research about calcium, magnesium, strontium, and zinc in literature. The compound calcium, magnesium, zinc 5 was synthesized experimentally, and it was determined that it crystallized in the orthorhombic cerium copper 6 structure in the PNMA 62 space group. Although the crystal structure of this material is known, the lack of information on its physical properties motivated us to this study. We studied physical properties of calcium, magnesium, zinc 5 compound computationally in experimental synthesized orthorhombic phase and analyzed the results. And all of the calculations were studied using ab initio calculation. ab initio method is a calculation method using the most basic crystal information, like that crystal shape, atomic types, and coordinates. WASP is a complex package program that can perform quantum mechanical and molecular dynamic simulations. The main purpose of density functional theory is to solve the multi-body interaction electronic wave function on the basis of electron density. In the study, calculations were performed using PBE parameterization in the AB initio-based generalized gradient approximation. Stress strain method used for predict elastic constants. First of all, a convergence test was performed to determine the NCAT parameter. In this and all the following states, we will use 684 gamma-centered Moncourse Hack-Caponate mesh. As seen in the graph, it's appropriate to use NCAT values less than 1 milli-electron-volt in total energy change per atom. Energy cutoff value is determined as 400 electron-volt after convergence test. These are the crystalline appearance of the compounds. The average position of atoms in the crystal is the main factor that determines many chemical properties, material hardness, optical and electronic properties. Let's parameters and structural properties were obtained as a result of energy minimization. The obtained parameters are listed in the tables together with the experimental data. We can observe that the obtained results are in agreement with the experimental data. In addition, data for the calcium strontium zinc 5 crystal are first published in the study. The elastic constants of solids report the mechanical and dynamical behavior of the crystal and provide important information about the solids. It also gives information about the hardness and stability of the materials. Second order elastic constants were calculated using the stress strain method. The material was found to be mechanically stable in the studied structure. Polycrystalline elastic modulus was calculated without the obtained elastic constants. Young modulus is related to the hardness of the material. It was observed that it was not very high in these materials. According to the criteria, the weaker hardness is also below 10 gigapascal. So we can say that the material has soft character by looking at both the Young modulus and the weaker hardness. Calcium strontium zinc 5 seems to be softer than the other. It's seen from Poisson ratio and Puff ratio that they have an ionic bond structure. From Bg ratio, it's predicted that calcium magnesium zinc 5 is brittle, and the other material exhibits a ductile characteristics. The other property is anisotropy. That's the change of elastic properties in the material depending on the orientation is called elastic anisotropy. For isotropy crystal, all values of Zener anisotropy factors must be 1, and percentage of AB, AG must be 0. All values differ from 1 and 0 shows anisotropy. The bulk modulus is less anisotropic for both compounds, while the shear modulus show more. In addition, mechanical modulus are visualized in 2D and 3D. The most anisotropy of Young modulus is in XY plane. As you see in shear modulus at second graph, the upper limit, the most anisotropy is seen in the XZ and YZ plane, while the lower limit on isotropy is most the XY plane. Poisson ratio is at the third graph in the XY and YZ planes. The upper limit anisotropy was very high, and the lower limit anisotropy was observed in all of them. When we look at the anisotropic graphs for calcium strontium zinc 5 and Young modulus, shear modulus, and Poisson ratio, all of them have high anisotropy in all 3 dimensions, as seen in these graphs. Lastly, I'll mention electronic properties of compounds. As seen in the graph, the valence and conduction bands overlap, and our materials show metallic characteristics. We can also reach this conclusion by investigating our state density curves. The materials are metal because there is density at the Fermi level. In addition, we can say that the contribution of zinc atoms to the valence electrons is high at both of graphs. It's observed that the conduction band is mainly composed of zinc and calcium electrons at figure A, and it's seen that strontium also contributed in the other graph. As a result, the structure parameters calculated for compounds were found to be compatible with the experimental data. The elastic constants were found by stress-strain method, and they have all stability criteria. To obtain electronic bond structures, show that the compounds behave as metals and materials are conductive. Calcium magnesium zinc 5 crystal has an ionic bond structure, and it's a brittle and soft material. Calcium strontium zinc 5 crystal also has an ionic bond structure, and it's a ductile and softer material according to calcium magnesium zinc 5. Thank you for listening.
Okay, thank you, Büşra, for your presentation. Do you have any questions? Do you have any questions? The participants, do you have any questions? If there's no question, I suppose I will finish the session because I haven't seen anybody from Russia. Are you here, Igor or Evgeny? Are you here? I haven't seen them. As far as I understand, they are not here. Let me give them minus. Okay. So, dear participants, your participation made us very happy, and I wish you all a beautiful and healthy day. For this organization, firstly, I would like to thank you to Gazi University and Professor Çiftçi, Professor Aydın, and of course, the organizing committee for all their efforts. And tomorrow, conference session will start at 9 o'clock in the morning. And have a nice day. See you, everybody. Thank you.
Thank you.
Okay, thank you.
And on behalf of the organizing committee, we want to share some videos about the boron. And
okay, let me see.
Yeah.
Thank you. And your microphone was not open.
and we continue with another video. And
Laboratories in Gazi University, right?
sorry?
They're in Gazi University, right? These laboratories from Gazi University.
No. Here is boron.
Oh, boring. Okay.
The hydrogen laboratory.
Okay.
There.
Very good center. As far as I recognize now. Thank you.
And then this one. And the final one. And this is short. And they finish. The laboratory is good and the equipments are expanded. And then thank you for your time. And thanks to the Boren for the video contribution to our Congress. And thank you.
Thank you. That was amazing videos. I haven't seen recognized. We have such as laboratories in Turkey. It was very good for me also. Thank you. Have a nice day. See you. Bye.
Have a nice day.